Welcome back. So in the last episode, we learned how to encrypt and decrypt using RSA. Unfortunately, if you just do it on each character one at a time, you're basically doing a substitution cipher, which is vulnerable to a frequency attack. So one kind of good practice is to block groups of characters together into one big number and encrypt that. Now, if you look around what people do out there in industry, sometimes it's done 8 bytes at a time. Sometimes it's done 16 bytes at a time. Instead of doing a fixed number of bytes, we're going to demonstrate a method here for doing a particular number of characters based on the key length. So if you have a public key n, some big number that's the product of two large prime numbers, the number of digits in that minus 1 is going to be the key length that we work with. So I've written a function that accomplishes this, and I'm going to show how it works, and then, or I'm going to show kind of what it does, and then I'll come back under the hood and show how it works. So we're going to set up RSA just in the same way we did in the previous episode using the GMP package. This part's the only part that's new here, really. So we've got some public key n, very large. To get the number of digits, we can take log base 10, and then we use the ceiling command to automatically round up for us. So we're going to have a key length of 30, and we'll work with that. Okay, want some text to work with. Thinking about blocks, we can think about Bitcoin. And so now we've got this. We've got some whole bunch of very this set of large numbers here. Each of these two numbers corresponds to an ASCII code. Not exactly. We've subtracted 23 as usual to make it more compact. At the end here, you'll notice we have a bunch of zeros. That part is the padding. We don't want to reveal how long our message is, so if we have any extra space, we're going to put a whole bunch of zeros at the end there. Okay, confirm that this works. Get our private key going. And now we can encrypt, and this is how it looks after you've encrypted, and even bigger numbers. Okay, very exciting. And now we can decrypt. And in case we don't want to eyeball it and see whether, it looks right. We see the zeros at the end there. But let's say we want to check more systematically. We can do a quick logical statement, and each block is indeed the same before and after the encryption process. Okay, and now we can use the functions that we wrote in earlier episodes to display the text. Where did it go? Data is permanently recorded in Bitcoin through files called blocks, and you see the padding comes through like this. Now we could write another function to clean that up, but there's really no need because this is what we care about. We can plainly read this. The warning message is absolutely harmless. It's just a function of the fact that you don't have exactly an even multiple for the blocks. That's okay. If you wanted to fix that, you would go back to the function two digits and try and clean up that one a little bit. Okay, let's see how the star of the show, the block function, works. It takes two arguments, one of which I call fuzzy text, and that is just anything written out in everyday language. What I'm going to do here is hard code fuzzy text for this time to be the same as our plain text. That way we have an example to work through. Okay, and our key length, if you recall, was 30. So here's what we're going to do. We're going to format it into ASCII. We're going to take off 23 so that no number is larger than 99, makes it more compact. Let's see if I can get this a little bigger. Okay. We have a couple of housekeeping items. One, I should learn to spell sudo more consistently. So the ASCII code for a space is only 32. If you take off 23, you're only left with 9. And unfortunately, that's only one digit. This whole enterprise that we're doing here is about counting digits. So we need everything to be 2 digits. So I've written this little if-else statement to make sure that 9s are actually recorded as 09s, or 09s rather, once it's in our function. Okay, so once we've done that, we can use a string split command and a couple other, the paste command like we've been doing throughout these episodes, to generate what I call techie text. And as you see, techie text is each number is stored separately. So each of these is half of that pseudo ASCII code. As we talked about, we're going to do blocks of length key length minus 1, and we need, how many blocks are we going to need? Well, it's going to be different each time, so I've written this other little expression here to do the number of blocks. So if we know that the block length is 29, we can just divide that into the length of the text, which what's the length of the text? 136. Okay. And so now we've got 4 point something or other, and the ceiling command automatically rounds up, and that's true even if it's less than 0.5. So now we know that we need 5 blocks, as we saw earlier. So we're going to write a loop. It's going to go through 1 for each number of blocks we're generating. And we need to grab the appropriate chunk of techie text. So we need an expression for where to start and where to end. Now, if you recall, if you have C 1 to 5, that gives you all the numbers 1 to 5. So you can just plug in that expression, C 1 to 5, where you see the iteration I, and then you can see if we're getting the appropriate values for every time we're through the loop. Indeed, those are spaced out by 29, starting at 1, and starting at 30, then starting at 59, and so on. And they should be ending, as appropriate. Let's see. So the chunks are going to end at 29. The next one will start at 30. The next chunk will start at end at 58. And so the next one will start at 59. And you see these line up perfectly. So that is exactly what we want. Another piece of housekeeping. So we're going to have these 5 blocks. If any of them start with 0, it's going to give us troubles. That block will not encrypt and decrypt successfully. This happens most often if you happen to have a space starting your block of text. So I've written this code here to replace leading 09 with 72, which is just an underscore. That's not going to take care of all scenarios. You might need to think about what to do if that wasn't the cause of a leading 0. But you're going to want to do something, even if it means converting, just plain a 0 to some other number in the appropriate range. But you got to do something to make sure you don't have a leading 0 for each block. And so that does it for the most common scenarios, but that's just something to kind of think about. Okay, now for the padding, or so I should mention, right? So we're going through the loop, and we're not going to have any padding to do the first time through. You're actually only going to have padding to do. I'll show you what temporary characters looks like at first. Looks like that our first time through. It's only going to be the final time through that we're going to have some padding to do. And so skipping ahead to that iteration of the loop, we see the temporary characters. All the final digits are NA, which is like not available or not applicable. That is how R stores missing data. Missing data is always a real thorn in the side of the researcher. You have to be very careful with how to handle it in each case. So we're dealing with it like this in this case. If we see an NA, we're going to replace it with a 0. And if we don't see an NA, we're just going to go with the characters that we've already generated. So we're going to do this. And you see we've got zeros, exactly what we want. And of course, in case you've forgotten, our paste command with collapse set to nothing in between combines all of that into one giant number. That's our block. And extra security, you might want to look at that for next time. That might, adding some noise to each block could be helpful, but we're not going to do that just now. We're going to generate each block, and we get to this when we have to store the block somewhere. And all this statement does here, it says, look, if I equals 1, if it's our first time through the loop, we're going to create a new thing called block list. And if it's not our first time through the loop, we're going to combine what we've already stored in block list with the temporary block or the block from the particular iteration that we're at. And that is the end of the loop, those little commands. So squiggly bracket closes out the loop. And then we're going to return that block list. And so that's all that happens in that function. Just to walk through once more, super briefly this time. We take some text, regular plain language, fuzzy text. We convert it to numbers. We take off 23 to make it more compact. We make sure that every number is at least 2 digits. 9 should be 0, 9, and any other characters that are that small. We need to make them bigger. We make every number, even though each code is really 2 digits, we make each one actually into 1. Or we store each one separately to work on. We count the number of blocks we need, or the block length first, based on the key length, and then the block count based on the length of the text as well as the block length. We loop through, getting the appropriate portion of the techie text each time. And we do a bit more housekeeping because we're worried about any of our blocks starting with 0. And then once we've run out of text to put into our blocks, we're going to pad the block with zeros at the end. And then we're going to store everything. Okay, and that is it. That's how you block. And once more, I'll show you the code for displaying it all at the end. Okay, and that's the introduction to good practices with RSA. Of course, there'll be more to come at some point, but that's something for now. Okay.